Actually, as editor, I just wanted to point out that since this is the Transpose episode, all your assumptions about it being in any particular order are completely.
Welcome to another episode of ArrayCast. My name is Connor, and I'm your host for today. And today we have with us 3/4 panelists, maybe one subject matter expert, and this will be a continuation of the topic that we discussed in our last episode. But before we do that, we're going to go around and do brief introductions. We'll start with Stephen, then go to Bob, then go to Adam, and then Marshall.
I'm Stephen Taylor. I'm an APL and Q programmer.
I'm Bob Terrio. I'm a J enthusiast, and I'm working with people on the J Wiki.
And I'm Adam Brudzewski, full-time APL programmer.
And I'm Marshall Lockbaum, creator of BQN.
And I'm your host, Connor, C++ professional developer, but I'm a huge array language enthusiast, learning several languages at once, and absolutely love having these conversations. So before we hop into today's conversation, I think we have 3 different announcements. We'll first go to Stephen, then Bob, and then Marshall for those.
There's a new page up on GitHub, awesomeq.org. awesome-q.org. It'll be in the show notes. Directs to a GitHub repo which lists experienced Q developers' recommendations for useful code libraries.
And on the JKAPL site, Roman Kashetson put together an interesting approach to trees, actually a pretty standard approach, but it's a good explanation of how you can represent trees in array language, specifically J. And as an additional thank you, at the end he mentioned the ArrayCast. And so those were one of the next things you could do if you were interested in the language, which I really appreciated. So he gets a mention.
And good news for BQN users on Linux, which is that just released, so in the past, you've been able to enable a dialog keyboard or an APL keyboard generally on Linux without installing anything, just from the command line, because it's packaged in a standard tool called xkeyboardconfig. And version 2.36 of this config includes BQN as well. So that's just out this past week. And I've installed it on Arch. They're probably the fastest at getting it out to users. I've installed it and verified that BQN is there. Over the months, other Linux distros are going to be picking up, so you'll be able to use a BQN keyboard right out of the box on various Linux distros.
Awesome. So yeah, notes, or links, I should say, will be in the show notes for all of that stuff. Be sure to check those out. Our show notes and our transcriptions are all awesome for each of our episodes, so definitely check those out if you're interested. And with those announcements and introductions out of the way, we are going to jump in a second into part 2, Transpose edition of our rank and leading access theory conversation. But before we do that, I've got a couple questions. And before that, we're going to throw it to Stephen, who's got, I think, just a small update on the news we had about Q licensing from KX last time.
Yeah, there was some speculation that the hiatus around licensing of the non-commercial free download of Q represented a withdrawal by KX of support for independent developers. And KX said that's not the case, and you can get a download of a non-commercial use personal study edition of the interpreter. I tested that since we were last here, put in an incognito application and got one within a few hours. So it looks all good.
Awesome. And I think the email, we'll have it in the show notes, but I think it's trial@kx.com.
You can just go to the website. You don't need to write an email.
Oh, awesome. So you can just go straight to the website. No emails required. Fantastic. Yeah. So for those that are looking into checking out Q, it still is possible. Just follow the steps on the website and you should be able to get a copy. And the 2 questions I have, the first one doesn't lead into the rank and leading theory conversation. The first one is, so it's sort of a tangent off of, I posted on the APLfarm Discord, is I believe what it's called, a problem that was problem number 1 of Leak Code episode 269. Details don't matter. But then a bunch of people posted different K, Q, and then Bob posted a J solution that was a short URL or a long URL linked to the J Playground. And it was looking fantastic. I haven't checked it in, I don't know, maybe over a month. And it was definitely an upgrade from what I had seen before. So just, yeah, shout out to the folks working on the J Playground. It's coming along nicely. But then in preparing for this episode, I was trying to find a APL wiki page that listed all the different sort of online REPLs or interpreters for the different languages. And there's one that shows all the ones for APL. And then underneath that, there's a link that says, go to a list of open source array languages, which I thought would maybe have those interpreters. And so it leads to two questions, sort of 1A and 1B. One, is there an APL wiki site that has a list of not just the APL interpreters, but like the K ones and the J ones, etc.? And two, we have to talk about, just for like a couple minutes, of on this list of open source array languages page, it's got APL dialects, which double digit 10 plus. Then it's got a section on K dialects, which it looks like there's 6 of. And then it says other array languages, where there's 3 entries for BQN, 1 for I, 1 for J, and then a couple other languages. And I'm a little bit conflicted on why J is relegated to other array languages, as is BQN. And in the APL dialects, I'm not going to call out any of these specifically, but definitely I think some of these, are more of hobby projects that I've seen in like little lightning talks at different language conferences. I will just stop talking and let maybe Adam or whoever, what's going on here? Questions 1A, 1B, go.
Yeah, well, so I don't really think it's the place of the APL wiki to be offering opinions on, which implementations are good and which are not. Obviously, it's focused on APL. It's the APL wiki. For K, I was probably the one that put in that header, and that's just because it's easier to navigate if you can see all the K dialects in one place. I didn't think of that as giving more prominence to them, but yeah, they do come first because that's kind of the categorization that makes more sense. I mean, I guess you could put other before. You could make K a subheading of other, I guess. I didn't think about that. Anybody can change this if they really feel it's going to be a big improvement, but the goal should be just presenting the information that's out there to the reader, as opposed to editorializing to the greatest extent that that's possible.
I guess that's a good point. I just, J, I feel like J is hidden there in a list of, as is BQN now, we got to.
Yeah, but I mean, these both do have their own pages as well, and they're linked on other pages when it makes sense. And so that's not the only place you'd see them.
And I'd like to add that I think, yeah, it's maybe a questionable whether the K should have its own table. Maybe it should just have a link to the K wiki, which has its own parallel page called running K instead of running APL. And it has long lists of web-based interpreters and implementations as well. And maybe, in fact, BQN shouldn't have multiple entries on the APL wiki and should just go to that page on Marshall's GitHub pages that talks about how to run.
Yeah, well, it's kind of set up to show the different source repositories for things, so it sort of makes sense that there are multiple rows for multiple source repositories. I mean, I put them all together so that you can see that they're just one language.
So it sounds like the solution here is that I've not acknowledged that this is a wiki, and I can just go
pretty much
and attempt to change it as much as I would like, and then have a response from, I don't know who the owners of this pages are. I assume Adam. I've seen Adam and Marshall have done a ton of the contributions to this site, but they can say, what is with the editorialization?
If you put something on the wiki, it's just on the wiki. It's there. It's content.
Stay tuned, folks. When you go to the show notes to click on this link, you're going to be like, well, what is Connor talking about? It doesn't look anything like you described, and that's because I will have taken my axe and we'll see.
Just remember what it says at the bottom when you submit a change. If you do not want your writing to be edited mercilessly and redistributed at will, then do not submit it here.
It's a wiki.
Yeah, but it is also a good policy not just to, revert completely back whatever change someone makes. Because obviously they made the change because the current page wasn't working for them. So if you think they've done something wrong, you've got to figure out how to make it better but still make it work for them.
And having done or getting into a lot of this with the JWiki, these kind of discussions are exactly what happens in a wiki. And the quality of your wiki, and I think the APL wiki is excellent. I don't feel slighted the fact that J isn't prominent because it is the APL wiki. But I think this is the kind of thing that you really have to think carefully about. And the nice thing about a wiki is other people can put information into it, and then it can get adapted or edited into something that might, if they have an extreme view, it can be brought back into more useful information fairly easily. And then, if it's really extreme, revert it. But it's everybody working together to try and provide a source of information. And I think that's the best way to look at a wiki. And the fact that these languages have wikis, I think, is excellent, and it becomes a pool. The quality of the people putting the information in and the information going in makes the tool much better. So with that, Connor, go for it.
Well, so what I was going to say is that, this is kind of funny, is that the thing that really prompted this was that J is right below Ivy, because the languages in the other array languages table are sorted alphabetically. And Ivy was like a little calculator language that Rob Pike, the creator of Go, that he wrote at one point, because he's a big APL fan. And it's like J is massive in terms of what it is compared to Ivy. And then to confirm that, they're both hosted on GitHub, and I was like, let's go take a look at these star counts here. And sure enough, J only has 497 stars, which is still, it's not none. But Ivy has 1,100, so twice as many. So that didn't really confirm what I was hoping it would. But so I think the moral of this is everyone should go and star the JSource GitHub repo on GitHub. And I mean.
But I think there are a fair number of people using Ivy as a little calculator tool, like it's intended, and who think that's a good system. And it's clearly a thoughtfully designed tool for that. It's got its own syntax and everything,
and it uses keywords. So admittedly,
well.
it's a lot easier to get started. Anyways, all right, enough. Or do you got one more thing to say, Bob?
Well, I was going to say thank you for mentioning J Playground. Joe Bogner and Chris Burke now have been doing a lot of work on it, and it is coming along really well. It's a really interesting thing. They've brought labs in. They're going to be able to do add-ons essentially at about half the speed of a regular J installation. You'll be able to do, I think, everything that you can do in J. You'll be able to do it online in your browser, which is way beyond what anybody thought it would be. And they're working through problems right now, but it's making big advances.
Yeah, I don't get how you got half speed with WebAssembly, because BQN came down like to a third or a quarter of the speed when we compiled CBQN with WebAssembly. So you guys are just lucky.
Not the first time we've been lucky.
Fair enough.
All right, so that tangent aside, so once again, I think this is the fourth time I'm saying this. Links for all of this stuff will be in the show notes if you want to check out any of these sites. And with that, we will go to my actual second question, which leads us into our part two of our, like I said, rank and leading access theory conversation. So if you're listening to this as a new listener, definitely pause. I guess we probably should have said this, a few minutes ago, but pause and go listen to the last episode, because this will be a continuation of the conversation we had there. And we did probably introduce a lot of the topics we're going to expand upon in that first episode, where we introduced sort of the idea of rank, the rank operator, axis, leading axis, trailing axis, leading axis theory, and sort of the differences in the languages. But we'll start this conversation out, and this hopefully is just a quick sort of answer, because I've spent a huge amount of time between now and the last time we recorded a couple weeks ago, thinking about the two different models of sort of BQN versus APL, and then I guess J is a closer to BQN in a sense, in that they both have the insert reduction operator and adhere closer to the leading axis theory, or maybe closer is not even the correct word to say there. And sort of the big eureka moment, to repeat what I said at the end of the episode, was the different ways to sum rows across languages. And I won't reiterate that, but the key thing that really stood out to me is that the slash in APL without the bar, that's really the outlier. And it's the one that when you come to APL, at least it's the one I would usually rely on most of the time. But the slash bar, along with the insert from J and BQN, are the ones that are sort of the more idiomatic. And go back and listen to Marshall's explanation of the slight difference between the slash bar and the inserts from J and BQM. But getting to my question is, at one point, it was talked about how that having the insert versions, the leading axis theory reduction operators, as sort of the base case is the intuitive, or maybe not intuitive or obvious, but it's the thing that makes the most sense upon reflecting on it, because it enables you to drill down as much as possible. Whereas if you use the slash version, that's starting at like -1 rank, so it's starting at the rows of whatever n rank array that you have, you can only drill down to the 0 rank atoms. And so my question is, how come you can't like drill out? Is that not actually possible? Could you not just go the opposite direction and weirdly define rank such that if you don't specify a rank, it works on rank -1. If you specify, like 0, it goes down, but then you could specify like -1, -2, -3, or like even drop the negatives and just, whenever it's non-zero, you're going outwards. Is that not a possibility? Like, I haven't really tried to implement it or anything, but like that's my question, and we'll go from there. Adam?
The concept is certainly a possibility. I remember suggesting this to Marshall a few years back, because I found that very often you do actually want that last axis, or you do want to deal with the scalars and so on, but sometimes you want to encompass more, you want to do more. I think the problem lies in it might not be clear from a definition what happens when you include more information. So here's an example. Multiplication. If we define multiplication in the scalar case, and then you have two matrices that you're multiplying together, then because it's defined in terms of scalars, then it's clear that you had just pairing up corresponding scalars with each other. And then we look at multiplication as it takes the whole array, but it really goes into each individual number. But if we start at the bottom level instead and define multiplication just on single scalars, then what happens when you scale up? What happens when you give it more information, when you specify somehow that it should get more? Maybe it will still do it element by element, but maybe now it becomes proper matrix multiplication. So you could make a system like this, but it's almost like a functionality selection then. You're saying you'd have to define it in a very different way. And I think Marshall used the word fragile in what I described. And it doesn't sound very rigorous. And everything, you'd have to define it multiple times. What happens in this case? What happens in this case? It becomes more of a special case than a generalization.
Do you want to add anything to that, Marshall? Is that consistent with what you're thinking in your head right now?
Yeah, more or less. It's hard to figure out how to say it. I think fundamentally the idea is that the rank operator only goes in one direction. It can only break things down and not build them up. So the old axis operator that Iverson was working with would let you do this, because if you had a sum that only works on a list, then you could say, well, break the array into columns and then sum those. But it turns out that for a lot of operations that don't work just like plain linearly, that's not really what we want to do. You'd have to change the whole design. The idea is that the plus slash without a bar already comes with rank 1, basically. And so if you add another rank to it, it's still, like at the bottom level, is splitting your input into lists. So it doesn't matter what you do with the input before that. You're going to be working on lists.
Well, you could have an operator
Well, so if you want an operator that takes a function that works on lists and applies it to matrices, then it has to pull lists out of the matrix somehow. And so it's never going to get to where you're working on the cells of a matrix.
Right,
really.
exactly.
I mean, I guess you could enclose each cell, and then you get a list of cells, and then apply it to that.
But then it would be, so the idea is, let's say you have this reduction, right? Plus reduction, for example. Then, and let's say it goes on the last axis by default. Then you could have an operator that that allows you to specify that if you feed it a matrix, that instead of just applying this function on each row of the matrix, it will take the matrix and split it into a list of rows and then apply the reduction between those.
Yeah, so what that would be doing is not rank works from the top down. So it pushes your highest level of the array that you see, it takes it down. So if you're working on a rank 5 matrix with rank 2, it'll make it so that you only ever see the rank 2 parts of that matrix. And what this would do would be to instead pull the bottom up. So you don't, you see a smaller rank, but what you see is like maybe a rank 2 array of rank 3 arrays. So it's pulling the bottom up so that the bottom level is a rank 3 array, and those are enclosed.
So I guess that this sounds way more complicated than what I had in my head, whereas like if we stick with your rank 5 and operate it on rank 2, in my mind, if you had a not a slash bar, so not a leading access theory reduction, if you just had your regular slash, which operates at -1 rank, specifying a rank of, whatever number it is, like -1 on your slash gets you to effectively like operating on rank 2. So it's just like, instead of starting at rank N and then working your way down, or because I guess it goes 0, 1, 2, 3, 4. Like I feel like it's like you can count down or count up, and like you can just convert whatever rank is to, like, I'm not explaining this well in podcast format. So if you have your leading access theory reduction and you're operating on a matrix, you can specify your reduction to be rank 0, rank 1, rank 2. I guess in BQN it'll fail on rank 0, potentially, because you said it doesn't allow that.
Yeah.
But like the default for the insert is to operate
the highest rank that you have
on rank 2, correct?
Well, on rank infinity.
or rank infinity, and then you drill down. But like technically you could design a rank operator that just starts at the other end and work its way up.
No, because the problem is the rank operator supposedly should be general, right? Which means it cannot inspect its operand. It just has to do some transformation and apply, and that's it, and not worry about what's actually going on. And if you give it a function that applies to the last axis, then it will always apply to the last axis, no matter what you do with it. And there's nothing that such a rank operator could do to force this function to consider the outer structure. It will always just drill in and do the last axis. But could this be done? Yes, it could. In APL, you have got bracket axis. That's exactly that. Right? Bracket axis, you can give it +/, which works on the last axis, and you give it a number in brackets, which is the dimension you want to work on, and magically it just works. The catch is that bracket axis has to be explicitly defined in the language engine for every single possible combination. And there's no general rule you can apply, because there's really nothing in common in the transformation between taking a last axis reduction and making it one of the previous axis reduction, and taking a last axis reversal and making it into some previous axis reversal. You can't really formulate a rule there. So the bracket axis is just ad hoc for every single operand that it can take, or if you call them operands, it's questionable. Every single function it can take or operator it can take, and it just has a specific meaning. And the only way that you can generalize this is by letting the user write code that takes that axis into consideration and defines the behavior ad hoc for his function. That is exactly what GnuAPL allows you to do. But the beauty of the rank operator is that you don't have to specify what will happen. It's already given.
Yeah, I think that makes sense. Well, so, and maybe we can feel free to skip this next question if it's not going to lend itself to anything understandable for the listener. Is it easy enough to describe the implementation of like a generic rank operator? Like, what is it actually doing when you say it's applying a transformation? So if we're sticking with a matrix, if you do like rank 0 versus rank 1 versus rank 2.
Yeah. So what the building block you need, because rank is kind of, well, rank is the simplest thing that even does this. The building block you need is a function that encloses the k cells of an array. So you'll give it the rank k. So if you give it rank 1, it'll turn like a matrix into a list of lists. If you give it rank 0, it turns it into a matrix of enclosed scalars. So you need that enclosed function. And what you do is you apply that function to both the arguments, all the arguments with the right rank. So that splits them up. And then you apply your function each on these arrays that are now split up. So that just applies to every pair of cells. And then you do a merge, or what's it even called?
A mix.
Mix, however you want to call it, to combine all those result cells together into one array.
Disclose rank 0 or disclose each. And
Yeah.
And one of the things that what I'm interested in is you keep mentioning all positive ranks, but in J you can do negative ranks as well.
Yeah,
well,
which allows you to separate items and whatever. You can essentially not worry about what the trailing part is and just break it up according to relative to where you're starting, which is kind of useful at times.
Yeah, every implementation I've seen has negative ranks too, but you can handle those as part of the implementation.
It's just
right?
computation.
You can write the code. I've written the code that takes the ranks and converts them all to the correct positive ranks.
So I think I'll try to rephrase it again. The steps you can go through, but it's if we break out of like the terminology and function and using functions from any of these array languages and just think of it as let's say we want to we have the first axis reduce and we want to apply it on the rows of a matrix. So we take the matrix and we chop it up into pieces, into rows. So now we have a bag of rows. And then on each of these items that are in our bag, we apply this reduction. Now the reduction can't apply on the original leading axis because that axis has been destroyed. It's gone. It's not there. Right? We only have a row, so we reduce each one of them, and now we've got a bunch of numbers. And then we take all these numbers that we reduced the matrix to and assemble them back in the order that they came from originally. And since it's a bag of individual numbers, that's called a vector or a list or whatever. Right? So it's a matter of splitting it up, applying the function on each chunk, and then stitch them all back together where they came from. That's all the rank operator does.
So that in that example, that one is like pretty straightforward because so you're doing a rank 1 first axis reduce in APL speak on a matrix, which means like if you're coming from a functional language, there's a function called chunk where basically because your 2D matrix is stored in row major order, you just do chunks of whatever the dimension of your rows are, and then you apply each operation. For the rank 2 case, where you're doing a column-wise operation effectively on your matrix, what happens there? Does that mean you're effectively doing a transpose and then a chunk, or are you doing something different? Because like transpose will flip it so that you go from column-wise to row-wise and then do the same thing. Because, and this all comes from, this is like our this is the like I don't know if it's what universe it is, but it's some kind of array podcast universe where like on my other podcast, Bryce and I have been talking about multi-dimensional iterators, and we have a couple more episodes coming out about that. And we've been talking, and Marshall, you have to come on now because I said something that you said, and then Bryce was like, "That's not right," and I was like, "Well, Marshall's probably right. I'm just saying the wrong thing that he didn't say." Anyway, so there's a bunch of crossover. We're going to show up in other people's universes. Anyway, so I've just been thinking a lot about like this, the default of an insert is to do column-wise. But actually, like that is striding element, like you're summing elements that are strided from each other. They're not actually contiguous in memory. And anyways, I guess this is the lead into. I just mentioned transpose without realizing that that's actually like the part 2 of this conversation. So Adam, go ahead, or Marshall, go, or whoever, Bob.
Actually, as editor, I just wanted to point out that since this is the transpose episode, all your assumptions about it being in any particular order are completely.
But we'll just reorder our inputs here afterwards. Well, you mentioned applying it on rank 2. So if we have a leading axis reduction and you want to apply it on rank 2, then conceptually you can on the matrix. Conceptually, what's happening here is we're chunking our matrix into subarrays of rank 2, of which there's exactly one, the entire matrix. So you could think of it as we take that entire matrix, stick it into our bag, and then we loop over it and we apply this reduction, leading axis reduction, to each item in our bag, of which there's only one, but it doesn't matter. Okay, and now that got reduced to a vector, because that's what happens when you reduce a matrix first axis. And we take that vector and we stick it right back into the collection where it came from. And since there's just one thing, so there's just one vector, so that's the result that you get.
So does that mean, if my understanding is correct, that a rank 2 first axis reduction on a matrix is less efficient than a first axis reduction on a matrix, even though they're functionally doing the same thing?
Yeah.
The rank 2 one requires you to do that.
Yeah,
enclosing,
it just
et cetera,
ignores
work.
it.
Well, you don't actually enclose, but yes, last axis reduction is efficient because the numbers you're summing in this case are contiguous in memory. There's no striding even.
Yeah, a decent implementation of the rank operator should see when it's the same as just calling the function. I mean, even if we're going to enclose that whole array and map over it and mix it, that's still basically no work because, creating...
Create a pointer, then follow it, then come back again and remove the pointer done.
Yeah, that would be a very small cost.
I missed what Adam, or I didn't understand what Adam said, though, about the first axis reduction on a matrix. The elements you're summing are contiguous. Like, that's not...
No, not first axis. Last axis, sorry.
Or last axis.
The last axis reduction, the elements are contiguous. Any other axis, that you have to have a stride.
But having a stride is actually better because that means the operation is more parallel. You can just take, if you're adding 2 rows together, you can take this vector, add it to this vector. If you're summing a single row, sum is, you can parallelize sum because it's commutative and associative, but at least on integers. For other operations, that might not be the case, so you actually do have to go one at a time. So generally, it's a lot better to do reductions along the first axis in terms of performance. You still might have the chance, like if you have many rows, you might actually want to do transpose sections so that you can then use vector operations and then transpose back, but that gets really complicated very quickly.
This has all been very illuminating, at least for me, the host. I'm not sure how the listener's doing, and I apologize if I've just caused massive confusion. But this is great. I just learned a lot, and a lot got clarified. I'm not sure if there's anything more we want to say on this topic, or at some point someone said, perfect transition to transpose, because I have no idea why that's important. In the space of leading axis theory. But
well, if you wanted to change your leading axis, that's how you do it with transpose.
All right, episode over.
Happy array programming.
Go ahead, Marshall.
So if you're doing a reduction on array, that's a case where you only ever work on one axis, period, and leading axis model lets you pick out that axis, and then you are done. You never need to transpose it around. Where you need transpose is if you're going to have multiple arrays and you need to align the axes together and shift axes around or something like that.
So you're saying you're doing something dyadically instead of monadically? Is that another way of phrasing what you just said? Okay. So is there like a concrete example that...
Well, even a monadic example can be given for where you need transpose first. So I think maybe a nice example would be, let's say we have a 2x3x4 array.
I was going to say, like, if we stay in the world of matrices and vectors, is there any use? Do you have to go to the world of cubes?
No, that's for sure.
Well, you never ever need dyadic transpose.
because they're the same. I mean, well, actually, you might use it for the diagonal. But
Well,
yeah.
there's only one transpose, one transpose that's not a no-op on a matrix, and there are no transposes that aren't a no-op on a list. So, and we should probably define this. So in APL, and also like if you're working with tensors, a transpose is rearranging the axes of an array in any order. So shuffle them all around. And of course, for a matrix, there are two axes. So how do you rearrange two things? Well, either you just leave them there, in which case, hopefully the implementation figures out, wow, the programmer has asked me to do nothing. I can do that.
Real fast too.
Or you swap those axes around. And so you can also, similarly, you can transpose a list, but there's one axis, and the number of ways to rearrange one axis are severely limited. So that's the idea with dyadic transpose versus monadic transpose.
Wait, that's the I mean, I understood everything you said up until that last. That's the difference between monadic and dyadic transpose.
So dyadic allows you to rearrange the axes in any order at all. Monadic, I changed it in BQN. In APL and J, it reverses all the axes completely. So you have axes A, B, C, D, and it turns them into D, C, B, A.
So it performs a reverse on a shape.
Yeah. So the transpose of the transpose in APL and J gives you back the original array. Always.
Yeah, that makes sense.
So in BQN, what I did is instead takes the first axis and moves it to the end, which is simpler generally, and it gives you more options because you can rotate it by any amount by transposing multiple times. It has a lot of cool properties.
And then you can apply transpose inverse to go back again.
I think we probably want to talk about, why you would want this completely arbitrary transpose reordering axes any which way before we go into why that particular kind of transpose might be useful.
Yeah, so let me bring this example. And I like using example of 2x3x4 array because we don't have unit length axes and they're all unique so we can recognize them. And there's also a human countable number of elements we got there. So we got a 2x3x4 array and we want to flatten it somewhat. And for that, I'd use Ravel. Now, BKN has other ways to do this as well, I think. But let's just use Ravel.
Well, you can merge two axes, but probably you just want to flatten them all.
So Ravel, it takes an array. It's kind of leading axis in the sense that it takes an array of any number of dimensions and it makes it completely flat. It just makes it into a vector. Okay. Now, there are different ways that we could flatten this array partially. Right? We could flatten it altogether. Let's just Ravel it. Done. But let's say we want to get it down to 2 dimensions instead by combining some axes. So we have a 2x3x4. We could combine the leading 2 axes. So that means we have 2 layers, and each layer has 3 rows, and each row has 4 columns. So in a sense, you have 2 tables, right? 2 matrices. And you could join them. So you have a single giant matrix that has all the rows from both matrices together. So since we had a 2x3x4 array, then it would be a 2x3, meaning 6. We get 6 rows altogether and 4 columns. Okay? So now we need to combine the 2 leading axes. If you try to Ravel, then if you Ravel the array as is, then you get a 2 times 3 times 4 elements in a single row. That doesn't work. If you try to apply the rank operator, then you can say, oh, I want Ravel to only look at some subarrays. So I can choose rank 0. That would add another axis. Definitely not what we want because it makes the scalars have an axis. We could do it rank 1 that Ravels all the vectors. That doesn't do anything. It's a no-op. We could do rank 2 that each of these tables, we have 2x3x4. So then we get 2 by, and then 3 and 4 gets Raveled out. That's 3 times 4. So we get a 2x12 array, which is not what we wanted either. Or we can do it rank 3. And now we're letting Ravel act on the entire array. And that we're right back to Raveling the entire thing. So now we get 2 times 3 times 4 elements in a single row, single vector. So how are we going to do it? So the way we can do it is we can see that we are able to use the rank operator to restrict the vision of Ravel so it can only see subparts of our array. But the axes that we want Ravel to see are the first two axes, and we can only restrict it to see last axis. So using transpose, we can move the axes around. If we take the first two axes and make them into the last two axes, which means that the original last axis becomes the first axis, keeping in mind that the last axis is the one we want to preserve, right? We want to still have 4 columns. Now we can apply Ravel to the last two axes together. That would be Ravel rank 2. And that gives us a 2x3 merged together to become 6 elements. Now we have a 4x6 array, but we actually wanted our 6x4 array. So we use transpose again to swap these two axes around, move the now trailing length 6 axis up to the front, and then now leading length 4 axis to the end. We get our 6x4 array. So we used transpose twice with Ravel and rank to do exactly what we wanted.
Well, one of the things I was going to say is this is when I think BQN has it as well, is you've got under, so that you can do this as almost like as just a two-step where you transpose and then reverse the same transpose coming back out. It's an under, so it's under transpose.
Well,
and you can.
Does that work in J?
Yeah, because you'd have J's going to end up flipping those last two axes too, so you'll get the shape you want, but you'll have the elements in a weird order.
So it doesn't work in J with under, not like that. It works in BQN because it's rotating the axis. And
so you want to put the first two axes last. That would be transpose inverse, but you can do under transpose inverse.
Yes.
And that is
and actually in J you don't have to specify all 3 dimensions to change the. You can do the. If you just give 2 dimensions, it just transpose. Shifts it over. Yeah.
But the concept is the same. Whether you're using under operator or not really doesn't matter. The important thing is that we're transposing twice. We're transposing so that the axes that we want to restrict our function to apply to go to the end. Then we're using rank to restrict that function. And then we're transposing back again if necessary. It's not always necessary to transpose at the end, but often is.
Well, Bob's going to stay on topic, but I have to say that J and BQN also do have the easy way to combine that first axis together. That's what I was talking about with the combining specific axes. You can do a join, or in J it's catenate insert, and that will catenate all the cells, that's the idiomatic way. And APL has you can do comma with axis. Some people would consider that some idiomatic, and some people wouldn't. So there is a way.
Yeah, but that doesn't matter. I'm using Ravel here because it's easy to understand how the shapes are changing around. I wouldn't do this using
that makes sense.
Ravel maybe, but I would use it with other functions where you don't have another way to do it.
So is the way to spell what we've been talking about in APL transpose paren, comma rank 2 and paren transpose?
You don't actually need parens, but and the transposing isn't right.
The transpose at the end of the first transpose that happens, which is at the right, needs to be a dyadic transpose. So that's why we're bringing up the dyadic transpose.
So the important thing is you want to move the axes around, right? You want to move the first 2 axes to become the last 2 axes, and the last axis to become the first, right? And the way you specify that is you tell transpose where you want your axes to move around. So now we have to be careful with index origin here. But you want the first axis to be number 2, and the second axis you want it to be number 3, and the third axis you want to be number 1. And then you can Ravel rank 2. So yeah, you can put that in parentheses if you want. And then you can transpose it back again. So transpose, open paren, Ravel rank 2, close paren, and then in index origin 1, it would be 2, 3, 1, transpose, and then your array. Or if it was index origin 0, it would be 1, 2, 0, transpose.
Yeah, that worked. because I was going to say before I was using 2 monadic transposes, and it was giving me a very odd order of things. So the real spelling is transpose paren, comma, aka ravel, rank 2, n paren, 231, transpose, and then your matrix.
Exactly. And so that 231, a lot of people get that wrong because how's it go? They think of it as where they want the x's to come from, but it's actually where the x's need to go. So the 231 means for the 2 is the first element. It means the first axis should become the second axis. 3 means which is in the second position. The second axis should become the third axis, and the 1, which is in the third position, means the third axis should become the first axis.
Yeah, it's the classic scatter gather. The difference between those two: one you're sending, the other one you're bringing.
Well, it's the inverse permutation if you want.
That's true as well.
So if you do a monetic grade on the 231, that gives you 312. And so that tells you where they came from instead. So that tells you for the first position, this axis comes from position 3. The second axis comes from position 1. The third axis comes from position 2.
J does it the other way around, though, right? It tells you where each axis goes to.
Really?
Yeah.
Wow, I didn't know. So wow.
So that's more intuitive, but the APL version is more general because it allows you to combine axes, which we wouldn't really call a transpose, but it's another thing that you can do with it. If you have, like even on a matrix, if you have 2 axes and you say, I want to send these to the same place, so you'll say 1, 1 transpose of a matrix or 0, 0. What it does is actually take the diagonal along that axis. So the index in the result turns into 2 indices in the argument that it's taking from. So you end up with a diagonal. So you'll get element 1, 1, element 2, 2, element 3, 3, and so on.
And the way J does that is slightly different. You box say 0 and 1, and as soon as you box them, it's just taking whatever times they're both equal. So box 0, 1 in a 2-dimensional matrix gives you the diagonal.
Oh, I see. So it's saying collect from both of these to this position.
Yeah, and it doesn't care about the order of the 0 and the 1 once you've boxed it. Doesn't make any difference. It's just going to look for the equality and take your diagonal. The interesting thing about that is you can take a larger number of dimensions and specify what diagonals you want to put together. So there's an interesting 50 Shades of J. We can link to it. It goes into great depth about this. And it's...
Is that functionality any different than APLs then?
I think it should be the same
Yeah,
possibilities.
I think you can have as many ones as you want in the left argument to transpose.
Yeah, and you can combine, you can say I want all these axes to turn into result axis 1, and all these ones to turn into result axis 2. You can do that either way.
Yeah, it just means that because it uses a flat left argument, then you can use grade to switch between the 2 representations when there are no duplicates, whereas the J version, you can't do that. So you would have to use key or something.
Yeah, there's a couple of, key might be a way to do that.
So in BQN, I did go with the APL way because it has the generality kind of built in, and it's simple. But the magic of having a 1 character inverse is that I pretty much get both. Because if you want to do it the J way, at least with an unboxed array, you just write out all your axes and you do transpose inverse. So that's pretty nice.
I have to say, I absolutely love the convenience operators like inverse and cells in BQN. There's something about when I see rank and then a literal number or array.
Well, and I guess technically each is a convenience operator too. So those are the 3.
It is.
And everyone likes each. not
in J. That's a good question. Because in both BQN and APL, it's just a double dot. I've always had the sense that the reason it's spelt out like that, so each, for those that are not familiar, in J is actually each, and it's what do they call it? The word each. Yeah, sorry, EACH. It's defined in.
I mean, the word each. It's a standard library word or something. Yeah.
Well, it's because it's a specific way of you're working with your unboxing, and then you're doing an under whatever you're going to do, and then you box it up at the end again. So the reason it's written out as each is because you could do different things with under, but it's very convenient to do boxing in J with under, and that's what each is.
Yeah, it's just under unbox.
Ampersand dot greater than. So the greater than is the unbox. The ampersand is composition.
Ampersand dot.
Ampersand dot.
No,
is the under.
That's under. Yeah.
Yeah, so the definition is under box, ampersand dot greater than.
So really what it's doing is...
It's initially unboxing. Whatever it's given, it unboxes, works on that unboxed version, and then reboxes it. And if you've got the colon afterwards and you're working infinite, it boxes the whole thing. Whereas if you've got just the single dot, then what it's going to do is it's just going to do the reverse of how you came in is how you go back out again.
And what was not to, well, I was about to say not to skip back, but that's exactly what we'll do here with this question. You said in J...
Welcome to Transpose.
Yeah, you said in J and BQN there was a convenience way of spelling the 231 dyadic transpose. You could just do a something on items or something.
That's only with Ravel, right?
This is, going back to the Ravel example. What was the way of spelling that?
It's catenate insert is how you call it in J. In BQN, it would be join insert. And so what that does is insert means you're applying your function across all cells. And catenate just combines them along the first axis. So overall, you get to combine all cells along the first axis. And this is pretty much the same as K's. You'd call it flatten is what they call the one that does.
It's concatenate reduction, right? In K.
Yeah. So it's comma slash in K, where I don't remember the names for the primitives, but you're joining lists. And K doesn't, like K naturally does things along the first axis because that's just the outermost layer.
And then in APL, the traditional way of doing it, using that bracket axis again, is comma bracket axis and iota 2 close bracket. And again, it's ad hoc, right? You cannot reason about this, so don't even try. It's just there is a definition that if you use the square brackets on the right side of comma, monadic comma, with some numbers for x's inside the square brackets, then this is what it does. It combines those x's together, revels those together. And then, but I'm actually proposing, in the middle of proposing a dialog, that we add a function, a monadic, I like to call it demote, which takes the two leading x's and combines them like this. And then if you want to combine more x's, you could apply it multiple times. And if you want to combine any internal x's, you could use the rank operator to do so. But of course, if you want to combine disparate x's, you would have to transpose first.
Yeah, well, that's exactly what the comma with axis does in dialog. It actually does, so you can combine any axes and they might be spread out across the array. But what it does under the hood is it just transposes them all and then does a mix or a split on some sort of split on the result of that.
Yeah, and this is where the difference between the reduce first in APL and the inserts in JMBQN show up. Because for the listener, I've been, to aid my understanding of this very simple topic, if it is not clear to the listener, I am being extremely sarcastic. I have been typing along in RIDE, J, and BQN. And for the convenience ones, catenate insert, which is like a little, looks like one of those styrofoam thingies that comes in a package, sideways S. Catenate insert, and then 2, I don't know what you call that, sort of underbar 3, underbar 4, shape range 24. That's pretty nice because basically it's just catenate insert and then your matrix. You switch over to J, and you can just do comma/i.234 because iota in J has the nice feature where you can reshape in the iota. I don't think BQN has that, correct?
Yeah. I really miss it when I'm writing code examples.
Right.
But I don't think I miss it any other time.
Yeah.
It's great for code examples.
And then APL, if you go over, and previously we had the spelled out transpose, paren, comma, rank 2, paren 231, transpose, and then your matrix, which is, compared to the two examples we just spelled out in J and BQN, pretty awful. If you switch to the ravel, aka comma, /bar, so axis first reduce, and then your matrix 234 shape iota 24, you don't end up with your 6x4 matrix of iota 24. You end up with 3x4 matrix of enclosed lists of length 2, starting off with 113, 214 going across. And I think this is what was explained in the last episode of how the difference between, this is the APL, the sharp APL way of doing things, and J's and BQN's is consistent with APL 2?
No, the opposite.
Or the opposite.
J and BQN are following sharp here. J is closely related to sharp APL.
Connor, if you take the BQN version, for example, and where you have that styrofoam thingy and the two and the double quote, if you stick an each in between the two, then you would get exactly like you would in APL. And the same thing goes for J, by the way. If you do this with an each.
Well, J would start boxing.
No, if you just do comma each reduce
a bigger change.
I.234 and J, that gives you the same thing.
Yeah, it does, but it's like,
Yeah, but that's kind of,
it's a lot different going from a simple array to a boxed array. Like there's this extra level where BQN's each, it was already taking arrays.
But basically,
so
there's an applied each
it's
in
still just
APL's
an array.
reduction
yeah,
that you cannot get around. I mean, you have to define it different.
Yeah, but J didn't have any boxes in the array before, so it's actually adding boxes.
yeah, it's changing the type of what you end up with coming back out, which is a bit more than, I don't think in APL you're changing your type at all, Adam, are you, at that point, with your each?
I don't understand what that means.
Well, I'm going from say, for instance, I had integers going in, I.234. I'm going to end up with an array of boxes now, because I each now will box what my result is. Can't get around that.
Yeah, but if I do the concatenate reduction in APL, you also get enclosures.
Yeah, so I mean, I guess it probably is not actually very interesting in this context. But like if you do minus each on a numeric array in J, you don't get that's not the same as just minus. It adds boxes to everything. So there's this extra level. Although APL and BQN are adding the extra level of array depth anyway, they're just doing it in the catenate rather than in the each.
And then you can, in APL, you can try.
Yeah, so that's a really subtle difference.
It doesn't really matter for what we're doing here. Because this is only because we're catenating things. If we're using any other function, that wouldn't really be relevant. And then, so the traditional way of doing it in APL is comma bracket iota 2 close bracket.
So I've got a question, probably because I don't understand necessarily the implementation of transpose as well as I probably should. When I actually do a transpose, am I copying the array into a different space? So I would be changing the stranding and everything as well?
The stride.
Well, the way
the strides. Okay.
Stride. The stride. Yeah. Sorry.
Yeah, every APL and J and BQN all actually perform the data movement. APL can sometimes do this in place. I don't know if J does it. It's not really it's not a hugely valuable optimization, and you can only easily do a transpose in place if you're transposing axes that have the same length. So sometimes it happens in place in dialog APL, but it doesn't really matter. And you are actually moving all the data, creating a new array that has this new ordering, as opposed to I think NumPy might actually do it like virtually, where it just where it basically says, well, now axis 1 is axis 2, and so on, because its array representation is complicated enough to have strides that don't go strictly in leading axis order.
And the reason I ask is because in that last ADSP episode that I listened to, that's kind of what Bryce was talking about, was that sometimes you need to change the order of your transpose. Well, for us, transpose, to be able to make full use of parallelization.
Yeah.
Because you're actually changing the order. Yeah.
And so that definitely can be the case. I mean, most primitives are, the actual primitive is going to be faster than transposing the array, but if you're going to do a lot of operations together, it definitely can be faster if you transpose an array first and get a more favorable ordering. Usually that's using plain leading axis operations instead of working with rank.
And that's what I've always been told, is that's your choice of what you put on the different axes is really important going in, because you can make your implementation much quicker if you choose them appropriately and not work against them through every operation that you do. And if you do happen to choose inappropriately for one section of what you're trying to do in your program, sometimes the best way to do it is to do a transpose, do all the stuff that you want to do, and then transpose back, because that'll still be quicker than trying to fight your way through something that's you're working against leading axis the whole way through.
Yeah, that definitely can be the case. And there are some, like the Fourier transform is one in particular, where often you want to transpose the data as you're working with it. So the Fourier transform does something along every axis, like the just basic implementation. You would require your input to have length that's a power of 2, and then you split it into a 2 by 2 by 2 by 2, and so on array. And you might be able to work with that, like you want to do something along every axis. So the two ways to do that are kind of to either actually apply this function with a bunch of different ranks, or to apply the function and then transpose one axis to the end and do it along all the leading axes that way. So it kind of depends on what your language has support for doing quickly, but a transpose can often be a good way to do that. And that's also VQN's transpose that just moves one axis to the end is a lot better for that, because after you do it enough times, you've rotated the whole array around.
I've been trying to code something to confirm my understanding of how this stuff all works. A one rotate on the find of shape of your matrix, and then doing a dyadic transpose. And I think it should work. I just haven't gotten it to work. At least that's how it works in BQN. So like the keys here are that dyadic transpose takes the trailing leading axis, moves it to the end. APL and J reverses it, correct?
Monadic transpose.
For dyadic?
For dyadic transpose.
Oh, okay, yeah.
Or sorry, yes. I'm trying to model the monadic transpose with a dyadic transpose.
So I don't.
I
think your find of the shape thing is kind of. You would probably want to take the rank, which in BQN is equals, and then do range of that, or iota of that. Because if you do classify of the shape, that's
right.
Like if you have two axes that have the same shape, that's going to give them the same number, and then you'll have everything will break.
Right. You can just do a range of rank, and then one rotate that, and then do a dyadic transpose instead of unnecessarily doing what I'm trying to do. All right, so I guess the closing question is, I mean, I'm kind of sad. This is like the most my brain's hurt thinking about APL in a long time. I've always heard about dyadic transpose as kind of like a joke in the Ray community. Assumably, there's utility in dyadic transpose. even transpose on higher rank arrays. I mean, matrices, I think most people can visualize. You just taking the two corners and flipping them like a bed sheet. Yeah, this is good? Double thumbs up to all this stuff, I guess. Like, you know.
Well, it's not just good. I mean, it's pretty much necessary, right? It gets really complicated if you were to write the corresponding code without dyadic transpose all the time, or transpose.
Well, it does depend on how many axes you have. If you don't work with data that has a really high rank, then you may be fine without transposing at all. You're almost definitely fine with just the monadic transpose.
Well, where really high means 3 or more, right?
Yeah, but I mean, even if you work with like occasional arrays of rank 3, you might actually be doing a lot of your processing at rank 2 and stuff like that. So you won't necessarily need to transpose those.
How often is it that you are explicitly writing out the left argument to a dyadic transpose as opposed to what I'm trying to do here in BQN, which is using the after operator to basically, define your left argument as a pre-processor function, like, the range on rank with a 1 rotate. So then you don't actually need to explicitly spell out that left argument. You can just, it's derivative of the current matrix, or higher rank array. Like, how is this classically used? Is it people spelling out like the left argument?
I'm not sure I understand this question.
Well, so like in our example, we spelled out 231 as the left argument to the dyadic transpose. But like what I was attempting to do earlier was like you could technically not spell that out and just do an iota on rank, so the shape of your shape, and then do a 1 transpose in APL to get that. Or sorry, a 1 rotate to get that.
Oh, so you're asking how often do we spell out what the left argument rather than computing it to be there? I always spell it out. I think, unless I'm trying to write some kind of utility where I don't know in advance what I'm dealing with.
Yeah, I think it's pretty rare to have a variable rank argument that you really genuinely don't know anything about, like what you want the axes to be.
The reason you would transpose is because you know the shape and it's not fitting what you want to do with it. So you would start with knowing the shape.
Well, like in the Fourier transpose example, you know the shape is all 2s, but you don't know how many of them there are. So, I mean, BQN lets you do that 1-axis transpose nicely, but I think in APL and J, your best option is to compute left argument for it. I don't know if there's a better way.
Yeah, I just looking at GitHub now has this. Well, you can be invited into it. This new code search thing, and so I searched for the regex of a digit followed by transpose to see what I could find, and it has 231 transpose. Then it has some diagonals, more 231, 213 transpose, and yeah, and 132 transpose. So. And in all those, yeah, in most of the cases where it has an actual left argument that's not just for the diagonal, then it's followed by raveling the leading 2 axes. So that's, but that was only in dialogues repositories, which aren't really representative of production code, I guess. If we search everywhere across all repositories, then we can find JFOD in some advent of code using a 2341 transpose. So that's an example where it would benefit.
That's still just transpose in BQN.
Exactly, that's what I was about to say. That is an example where you would actually want BQN's transpose. I find one here that says 102 transpose. So that's flipping the first 2 axes.
Yeah.
So there.
So that's BQN lets you drop the trailing elements from your left argument, so you can write that as one transpose.
Yeah.
And Jay, you could have your dyadic transpose. If you just put a 0 in front of it, it's going to move that 0 axis to the end, and if you can do it that way.
Oh yeah, so that does do the BQN thing nicely, but that doesn't do this one that we just mentioned.
Then I found an interesting example here. 1, 2, 3, 4, 4 transpose. That's just combining the last two axes. That could have been written as a
so that's 0, 0 or 1, 1 transpose with rank 1.
Rank 2.
So it's 1, 1. Yeah. It's 1, 1 jot transpose, rank 2.
But then there's a real example. 0, 1, 2, 3, 5, 4. Look at that. That's just transposing the last two axes, right?
Yeah.
So
which is transpose rank 2.
Yeah.
This episode has, you got to, like, I am now the listener, effectively. I'm no longer the host. And, like, all I'm hearing is, well, we got a couple examples here. We got 1, 0, 2 transpose. Oh, that's actually in BQN. Then that's just a 1. You can drop the trailing. Now we got a 0, 1, 2, 3, 4, 4 dyadic transpose.
It's perfect, isn't it?
That's a good example we got there. That's a class.
I found one.
Oh, look, this one. We got a 2, 3, 1, 4, 4. That's actually classic. I remember that one from 2017. And I'm just sitting here being like, what has happened to my favorite language? Like, we used to work linearly, you do one operation, then another one, and now I just feel like I'm falling, like, Doctor Strange when he goes into the glass thing and his thing, and he's falling and things are breaking. I'm just like, we're in the mirror dimension, and and Adam and Marshall are just going back and forth, speaking this different language. Oh, yeah. Well, no, yeah. And Jay, Jay doesn't have that. Oh, look, a great example. I'm just like, you guys are literally speaking a different language now.
No, I mean, you can go make the search. We'll put a link to the search, and you can see that there are actually some uses of it, but it's pretty rare. It's true.
The point is that when you write out all these numbers, it's like, how do you understand that? You have to read all these numbers and figure out what they're saying. If you say transpose rank 2, you know what that does, right?
Yeah.
Maybe.
Sure.
Adam knows what that does.
I mean, then I mean, you have a collection of matrices and you're transposing all those matrices. That's pretty straightforward, I would say. But there are some. I mean, there's something here. Sudoku solver. It seems 1, 3, 2, 4 transpose. So that's like
back into it.
That's interleaving the axis. That's a real.
Yeah, that's a complicated.
That's a real hardcore usage of transpose where you're.
Well, it swaps the two middle axes.
Yeah.
But I don't have an easy way to write that. I mean, I guess. No, you could use one transpose cells.
1, 3, 2, 4 transpose.
So, there we go.
But to answer your question, Connor, it is pretty rare, right? It is masterclass type things, and it's maybe even indicative, possibly, of you having structured your data wrong to begin with. And ideally, you want to avoid this kind of transposing.
Yeah, and I feel like you just mentioned there casually that's why we have. You can combine rank with transpose, which is we haven't even really talked about. We've talked about transposing before and after, aka doing rank operations like under transpose, but we never really mentioned the fact that you can transpose and you can modify transpose with rank, which I guess for the example that you painted out wouldn't work, but for certain cases it could.
Well, if you think about it, say you have 2, 3, 4, right? And you apply rank to transpose in that case, you're just going to transpose the two tables.
Right.
They're not going to affect each other. They're just going to be transposed themselves. That's all that you're doing there.
Well, this is maybe too big an intervention to handle in this episode, but I did write a paper some years ago about an application that was working with rank 8 arrays and using dyadic transpose to as an alternative to what in another implementation would be non-trivial or a lot of SQL queries. So a rank 8 array could be represented as a flat table with a lot of index columns. And so in APL, you can go and say, I want this index on that axis, this index on that axis, and this index on another axis. And it's kind of equivalent to doing a select where these indexed columns indicate where you are. But the challenge was to keep the application logic readable with all these indexes and axes. I'll just kind of bookmark it here and leave the URL for the paper in the show notes.
Yes, it sounds like there's definitely is some utility in this stuff for sure. It's just literally mind bending.
It's array bending.
Which is worse.
Yeah, I'll say the same thing as I said at the end of the last episode, is that I've made it a solid 2.5 years without not only understanding dyadic transpose, or even transpose on anything higher than a matrix, a rank 2 array. I can't even think of, although mind you, I'm not writing production code, 6 or 8 hours a day in APL. I can't really think of a time now having this, 20% in my tool belt, because let's be honest, gonna have to listen to this episode a couple times and then play with it a lot more to really fully understand this. I can't really think of a time that for simple problems you really need to reach for this. It's probably
Well, your last ADSP though, that's exactly what Bryce was talking about. Is if you do a transpose, you can break your the things you're working on up in different ways and be more effective when you try and go parallel.
Yeah, but generally you would just do one like monadic type transpose where you're swapping two axes. So yeah, dyadic transpose. If you're really working on those rank 8 arrays and your data is 8-dimensional, then you're probably going to need some pretty complicated transposes at some point. But most applications work with rank 1 or 2 arrays, and even just working with rank 1 is often fine. So in a lot of cases, you don't need anything complicated.
Yeah, my mental model is, most of the things are just sort of data flow operations, one input, one output. There's certain ones like outer product and reshape that can explode or add some dimensions, and reductions, reduce dimensions. But like this is a whole new, a dyadic transpose with, a 3-element array or 4-element array that's doing something that like completely is gonna, if you're going through visualizing, oh, what's my intermediate state? And then you hit that one, it's just like, woo, you flipped upside down, or now you got your head underwater. So yeah, definitely it's, what did someone refer to it as, a masterclass glyph?
I think once again we should congratulate the listener.
the one who's still with us.
Yeah, congratulations on making it this far. And don't worry if it's a bit much, because lots of people have been successful APL programmers and used APL or other array languages a lot and haven't really done a whole lot of dyadic transposing.
All right. With that, I guess we will tell the... Well, first, once again, thank you, Marshall, for coming on. As always, these conversations are great. And with that, we will say happy array programming.
Happy array programming.